Thank you all for coming. Just out of curiosity, how many people have been to a talk by me before at SQL Bits? Okay, thank you for coming back. For those of you who haven't, I'll do my bio in just a second. I was looking for an interesting talk that I thought would be kind of something different, and I thought I would give sort of an architecture talk today that explains a little bit about why SQL Server and SQL Azure and Synapse DW is fast on analytics. And this talk is intended for those that want to learn more about how SQL works, but you don't have to have a degree in computer science to truly grok all this. The intention is to make this accessible. So I encourage you to interrupt me and ask questions. There's no dumb questions. The stuff that I'm trying to cover usually takes several years of study to actually really grok. So please don't think that if you haven't done any of this before, you can't ask any question. I'm perfectly happy with that. The intention really this whole talk is just to give you a sense of the amount of work that we put into trying to make SQL go fast for you so that you can focus on your business and not have to necessarily worry about the details as much as I have to worry about the details. So with that, I will get started. I guess I didn't have a bio slide, so I'll tell you about my bio slide first. I've been at Microsoft 25 years. I ran the releases of SQL Server 2016, 2017, and 2019. Since 2019, I've been building an engineering team where I live in Austin, Texas. And one of the areas that I work on that team is advanced analytics on new hardware. So I work with Intel, AMD, and other advanced hardware options to try to figure out where does SQL Server and the other variants of SQL go in the next several years? How do we make computation go fast on hardware that's coming out 3, 5, 6, 7 years from now? And then I work my way back to what does that mean for a database architecture? So let's go back in time and we'll get started, not exactly at the beginning of where SQL Server was, but I joined the SQL Server team about the time when SQL Server 7.0 was happening. And at that time, it's roughly the era of the first Pentium chip from Intel. This is a picture of what that chip looked like if you put it under a microscope. It is one core, and at the time it was one of the first chips to do something called superscalar operations where it might be able to execute 2 instructions simultaneously. So it was kind of a big deal back when it came out. It didn't have hyperthreading like we have today. It didn't have any fancy stuff. It was 60 megahertz or 66 megahertz if you bought the fancy version. The lines are 800 nanometers in size, which is pretty big by today's standards, but at the time it was considered revolutionary. And we used to run SQL Server on this. You know, back in the early days, this was what SQL Server would run on. If you bought some server chips, you got a couple of these. Hopefully you got 2 cores and 2 sockets and 4 cores maybe and 4 sockets. And it was really, really a big deal. It had a cache of 32 kilobytes, it's called an L1 cache, so it would load up data from main memory, and it's a little faster to load it from this cache than from main memory. And ultimately, this was all we had. So if I were to go back and remember what my day in a life of being Conor, the software engineer, was, to build SQL Server, to be able to do our daily work, took 25 minutes to do a clean build. So we would load up, say, yep, I'm going to get started today. I'll build SQL Server, then I'll start debugging something. It was immediately several cups of coffee before you actually got to debug something. So we made some progress. I'll cover that in a future slide. But if you're going to run this in production, back then we didn't have SSDs. So you'd have rotating disks, and they would have a latency to go do an I/O to the disk. And if you wanted to run these in a server configuration, you had to get arrays of rotating disks. And then you'd need multiple controllers eventually to get the bandwidth to be high enough to be able to run one of these processors. Because at the time, the CPUs were fast, but the disks were slower. And so you ended up needing to kind of have arrays of disks to be able to make everything work. It took a lot of power, and it was very noisy. But that was our day back when we were doing things at this time. So when we built SQL Server, the main thing I want you to keep in mind is this was the class of machine that we used in the original architecture. It's actually earlier than this, but this era of computer chip is what we used when we were building SQL Server. A lot of the things that you use today are still there from when we built this code on this class of server. We did a lot of really, really good work back then to figure out, okay, how do you make sure that something runs as efficiently as possible? And there's all sorts of tricks you can do, similar to maybe building an operating system, about how do you make sure that you use just the right number of instructions and go as quick as you can on this class of hardware. Now, the nice part about it is a lot of those techniques translate to modern hardware, but not all of them do. So I wanted you to get a picture that SQL Server as a code base is not a static thing. It actually evolves over time, and every single release we have to go test and twiddle things and test some more until we get it to actually run really, really well on modern hardware. The other thing I want you to keep in mind is that the way that hardware changes over time also changes. So the things that get faster don't get faster at the same rates, and as a result, you might have some areas where you've designed your code base one way, and then as the machines start to evolve, you lose your advantage compared to your competitors, and you have to go rethink the design and alter it underneath the covers. Now, we don't usually talk about this level of detail. We just kind of show you some benchmark numbers and call it good. But I wanted you to get a sense of this because as we start looking at what does it mean to actually build something that runs fast on modern hardware, I wanted you to start with a picture of kind of where we started, more or less, and then give you a picture of just how complex modern hardware is compared to even this, which was pretty fancy at the time. If I were to give you one picture here, it's just, this is one core, and today, like even on your laptop, you have many cores. So back in the day, this was what you'd buy, and you were really happy if you had it, but this was my life back when I graduated from college, essentially. So this is a picture, color annotated, of a modern Intel CPU. The name of the microarchitecture version is called Ice Lake SP, and this particular one has 28 cores on it. This would fit in a single socket, just like the last picture I showed you, but it has 28 cores, not one core. Each of the cores is hyper-threaded, meaning they can run two things at the same time, and when you expose them in Windows, you would see that these are two logical processors, not physical processors. So this would show up as 28 times 2 physical processors on a single machine. This uses a 10 nanometer process. Remember the Intel one that I showed you before had 800 nanometers, so the features are much, much smaller. The size of these dies are comparable. This particular machine goes 3.7 gigahertz, this chip I should say, whereas the last one was going 60 megahertz, 66 megahertz in the fancy version. Whereas before we had a 32K level 1 instruction cache, we have that as well, sort of, except now they've separated the instruction part and the data part to each have their own cache. And so you have 32 kilobytes for the instruction cache, 48 for the data cache, and there's actually 3 levels of cache now, each with increasing size and slightly lower speeds, to try to deal with the fact that since the Pentium chip came out, the difference between the clock speed in the CPU and the speed of main memory has gotten substantially different. So now the cost of having to go to main memory is really, really expensive, whereas maybe it might have been 30 cycles or 20 cycles on an old Pentium CPU. Now it's hundreds of cycles on a chip going this fast. So the cost of not having data in your cache is extremely high compared to what would happen before. If you are a CPU and you try to say, hey, I want to load this value, and it's not there, you block, and you have to wait until the memory loads up. It does all sorts of tricks now to try to hide that from you, so it looks ahead and tries to execute instructions that haven't started yet, speculatively, to see, oh, you might need this value. So I'll try loading it up just in case so that when you get to it, we don't stall the CPU. This ends up meaning that there's a lot of complexity in this particular chip to deal with all the things that you need to make a computer go fast. It also means that it has a lot more smarts in it. There's a lot of transistors that are spent trying to understand different kinds of workloads and to tune them automatically without you necessarily knowing it. So, for example, as I mentioned, it can reorder instructions. It has the ability to execute speculatively different kinds of instructions or cache loads. It has other kinds of instructions that it's added that can do fancy things. I'll explain some of those in a bit, but we have the ability to do operations on several values at the same time. These are called vector instructions. And in addition to that, we're executing many instruction parts at the same time. Whereas in the Pentium, you might be able to execute 2 instructions at the same time. Here, this is executing parts of up to 100 or more instructions at the same time, trying to figure out how to hide latencies from the user's application. Any questions so far? Okay. One other clarification. This Ice Lake CPU is a modern CPU. It's not the actual most recent one. Intel came out with a server chip in January called the Sapphire Rapids CPU, which is the successor to this, which is even more complicated than this, but I don't have a die picture to show you today. but I do have some numbers later where we're using one from Intel that they gave us. All right, this is a little complicated to see, perhaps, so I'll try to explain it. The idea behind this picture is to show how many transistors are in each generation of CPU. The main thing I want you to understand is just how insane the amount of work that they do in the hardware layer to try to add more and more detail into that to simplify you, the human's process of writing an application, or me, the SQL Server application's process of writing SQL Server for you. To give you a picture, roughly in the middle there, at about 5 million or so, just under 5 million transistors is where the Pentium is. So it's about halfway up, and roughly 1994-ish on the picture. And that's not the first SQL Server version, but it's maybe the first one that we'll reference for today's talk just as a reference point. And if you were to go all the way up to where we are for the Intel Ice Lake processor, it's past the end of the chart up there. It's near where that AMD EPYC Rome chip is in terms of complexity, where it has not 3 to 5 million transistors, but it has something on the order of 30 to 50 million transistors. So the amount of complexity that's going into the chips that you use to build database servers has been going up substantially, and the amount of value that they can add is very, very high, but it also really exposes the fact that these have gotten complicated because there's a lot of factors that go into how fast can you make a processor, and what limits are there to how fast you can make a processor, and then what do I, as the database engine architect, have to do to think about what to do about those limits so that I can make your database engine go faster each version of SQL Server that you buy. Okay, I need to introduce a concept that you would study in a computer architecture class in college, and it's called instructions per cycle. And it's a little funky because you would ordinarily think of a CPU as, okay, I have an instruction, I execute it, it takes maybe 1 cycle to execute each instruction. That's not actually how it works. If you have a load or a store to memory, it might take 100 plus instructions if it needs to write all the way out to main memory. So some instructions can take 1 cycle, some instructions can take several cycles, some instructions can access memory and then potentially take a very long time, depending on what kind of instruction you're running and how you execute it. So one of the metrics that chip designers use is how many instructions can they retire on average per cycle. And this is called instructions per cycle. So what that really means is they're trying to execute many instructions in parallel, and they're trying to figure out how many can I get off the queue so I can move on to the next ones. So you can think of it roughly as an efficiency metric. If generation 1 of a CPU runs in X instructions per cycle, and then you can get to 1.1x in the next generation, that would be a huge gain. 10% improvement in instructions per cycle from one hardware generation to the next is not usually the case. This diagram tries to give an example for the Intel chips, AMD's has similar kind of graph though, of what types of improvements you get from each hardware generation to the next when going from one version to the next of the CPU. And this goes over the course of a decade or more of Intel's chips. And you can see here there's the yellow bars, which describe the rough improvement per the prior version. And then overall, the cumulative change over all the sum of these microarchitecture versions. So if you went from the first one, which is this 90-meter Dothan process, all the way up to Ice Lake, which is the picture that I showed you a diagram of earlier, you can see that the instructions per cycle gain total is 2.2 plus 2.4, which really means that if you were to take those two versions of the CPUs and run them side by side, the Ice Lake one would be retiring instructions at over twice the rate of the older one. That's a good thing, in the sense that that means that they're getting better at figuring out what kinds of applications are built and how do we make those run efficiently on each version of the chip. That includes database applications, but obviously some applications are written in different ways and they can all have different logic, but it also means that if I, as the database implementer, go and look at what parts of the chip go fastest, sometimes I can translate the problems that we're building inside of SQL Server to go faster on the newer versions of the microarchitectures than I could on older versions. And we also do that work, which means that sometimes we can do better than that 2.2, 2.4 number that you see there on the right-hand side of the graph. All right, So one of the problems that you have in building database engines, this is actually not specific to database engines, is how do I count bits? So if I have a bunch of memory, I want to know how many bits are set. So sometimes if you see hash bitmaps in your query plans, we would want to know how sparse is the bitmap. Is it 90% set, 90% unset? And we might do something different based on how many bits are there, because we can make the query go faster if we know, oh yeah, most of the time you're going to hit on the bitmap, so we should do something that looks different in terms of algorithm, in terms of how fast we go to check it. Other times it might be very sparse, and therefore we know it's very selective. So bitmaps are one example of where we use this. We use this for space map allocation. There's tons of things that we use bitmaps for in database engines. But this example, ignore databases for just a minute. Let's just assume I had a bunch of memory and I wanted to count bits. For those of you that are not familiar with the internals of computers, they use base 2, and you would have different representations of 2 to the 0, 2 to the 1, 2 to the 2 to represent how many bits are set. So if I were to have the value 1, that would have 1 bit set. The value 2, which would be 2 to the 1, so I would have 1, 0 as the representation of binary. That would have 1 bit set. The value 3 has 1, 1, so that's 2 bits are set. The value 4 has only 1 bit set. It's 1, 0, 0, et cetera. And so ultimately, when you start doing bit counting, you want to know how many bits are there. And it might be for a value or for an object like a bitmap. We use them for a lot of things in terms of bitmaps. So one of the problems that you study when you're trying to figure out how to make a compiler work really well or a database engine go fast is what algorithms can you use to count bits efficiently? Because there's different ways to do it, and depending on how you write the code, it might go fast, it might go slow. I wanted to give you an example that hopefully is separated enough from building the core of a database engine so you can understand the kind of choices that we have to make internal to SQL and how this goes into the performance of your queries. So I put together a small example and I ran it on the most up-to-date hardware that I have. So we have a server that we have from Intel, which is this Sapphire Rapids CPU, and it's the newest CPU out there. It's extremely fast. It has hundreds of cores. And I put together an example to say, okay, I want to go check for, I think it was 8 billion bits. It was 8 billion bits, something like that. How many of them are set? So I put together an array and I tried 4 different ways to count bits. And I'll explain each algorithm roughly to hopefully give you a sense of how they might be very close in terms of what you think they might be in code, but how they differ in terms of performance. So one way to check bits is if I have a 64-bit CPU word, I might say, here's the first bit. Okay, check that. Is it set? Yes. Okay, great. Check the next bit. Is it set? Yes. And keep a running counter as I go through each of the 64 bits in a CPU word, then move to the next 64 bits and do that again. The graph on the left here, the bar on the left, is describing that algorithm. And it takes about 4.2, 4.3 seconds for me to do 8 billion bits that way in SQL, well, in the test example that I wrote. The next thing you can do, in fact, when I first started at Microsoft, this was one of the interview questions that they used to try to see if your young developers knew what you were doing was, hey, how do you count the number of bits in a word? And the easy answer was the first one. The fancy answer at the time was, oh, well, if you have 256 numbers, you know that each of them will always have the same number of bits. So you could just have a lookup table and say, okay, the bit 0 has always got 0 bits, bit 1 has 1 bits, and then you could look up into this array, and it would tell you how many bits you have. And this was the smart answer at the time. And you can see it is faster. It's about 2.6 seconds to do a byte lookup table. And that was the efficient answer back in the day, 25 plus years ago. About 15 to 10 years ago, most of the CPUs that came out had a new thing that it would do an instruction called pop count, population count. And it was a CPU instruction that said, given a word, either 32 bits or now 64 bits, just give me the answer for how many it is. Basically, they did the lookup table in the chip because they knew that people were doing this a lot. So they built this instruction, and as you can see, now it's going 1.3 seconds. So now we're several times faster than the original solution. And then finally, the most recent versions of the server CPUs that Intel makes has a new instruction which is called vpopcountdq, which is basically a vectorized pop count to say, I want you to take 512 bits and do pop counts for each 64-bit set in parallel in one instruction. And therefore, I can go 8 times roughly as fast in terms of computing these and load them all up. And as you can see there, if I do that, I'm down to roughly 600 milliseconds to do the same problem that originally took 4.2, 4.3 seconds before. So if you understand how the chip works and how it works efficiently down at the level of the assembler, you can go do things like this to make your database engine go fast. And this is more or less part of my daily job, is to go find ways to do this so that we win on benchmarks and you guys are happy. Any questions? All right. Okay, the next thing that I want to explain to you, I'm going to explain outside of a CPU first, and then we'll talk about the slide. Let's say that I have a 17-year-old daughter, and let's just say her friends are more important than I am to her on a daily basis, and I'm like, hey, are you going to be home for dinner? And she's like, I don't know, maybe. And therefore, I need to figure out, should I make dinner for one or for two? I don't know. So I stall. I figure out, well, either I should make a dinner and then just save her some, or maybe I should just order something and then deal with the fact that she hasn't told me if she's going to actually be home for dinner or not. Anyone been through a similar situation? Yes, this is not unheard of, right? Well, CPUs have the same problem in that the programs that get compiled don't tell them what way you're likely to go if you have a conditional branch. If you have an if then else, it doesn't, it guesses which direction you're going to go. And it spends actually a ton of time. There's actually a whole area of chip design on how do you guess what way you should go in a branch. And then they do things like look down one side of the branch and start executing instructions down that side of the branch. And they may be right, they may be wrong, and they have to figure out how to undo things if they were wrong once they figure it out. Because remember, these are executing lots of instructions in parallel in different little bits. So it's trying to figure out how to go faster here so that it can move that instruction per cycle number higher each and every release. Now, once you look at the code here, while column is less than end, do something, eventually, if you were guessing that you'd always take the branch, you're going to be wrong. And at the end, you don't take the branch, and you fall out of the loop, and you move down. And that's how C works. But the main thing that I want you to take away is as CPUs have gotten bigger and have more cores and are more superscalar, meaning they're executing more instructions in parallel in little different bits, the cost of guessing wrong gets more and more expensive. So they're going to spend more and more transistors trying to figure out how to not guess wrong, but they're always going to be wrong sometimes. And that means that your overall efficiency about how quickly your program works, or your database engine in my case, really boils down to what do I have to do to figure out how to make sure that I don't have as many branch mispredictions. And if I can make my CPU not mispredict a branch, then I can make it go faster on average. So the solution is, don't ask your daughter if she's going to be home for dinner. Tell her she is going to be home for dinner when you can. In other words, write algorithms that don't have as many if statements. And if you do that, you can make your database engine go substantially faster, which is exactly what we've done. Okay, so I want to summarize sort of at the highest level, like what do you want to do if you want to make your database engine go really, really fast? First, use the modern instructions that they provided to see if you can take algorithms and make them run more efficiently than what you could do with your own logic. Second, don't do conditional operations if you don't have to. Third, figure out how all those caches work and figure out how to build data structures and algorithms that can map really, really well onto those data structures and algorithms of caches so that you can be very, very efficient in not having misses for the CPU at each level of the cache. The next thing, which I haven't done an example on, is if you want CPUs to run really, really fast, you don't want them to wait on other CPUs. And if you have all those CPUs trying to talk to each other and share some structure, then it doesn't go very fast. So your next solution is don't do that. Don't ask questions. It's the same conditional branch question except across CPUs. And then the last thing you need to do is figure out, okay, in each generation of microarchitecture versions from each chip manufacturer, you have to figure out what it really does well and then see how do you map what you do to the sweet spot of that processor. And if you don't do that, then it might still work okay, but it doesn't necessarily mean that it's going to win on a benchmark for you. So we spend a bunch of time working with each of the main vendors trying to figure out what are they doing, what parts of their chips work certain ways, and then what can we do to take advantage of that so that you don't have to. Basically, we can worry about that problem. Okay, any questions? Thus ends the main microarchitecture part that I've given you that usually takes 1, 2, 3 semesters of advanced college. You now are all experts. Congratulations. All right, so now we're going to start talking about features inside of SQL Server. So I want to make sure that I get everyone up to speed. SQL Server has this thing called batch mode. Batch mode is one of 3 execution engines that we have on how we execute queries within SQL. It's traditionally associated with our column store index, which is a compressed indexing structure intended to make analytics queries go really, really fast. It doesn't only run in that model, but for today, think of it as the main way that you would get to it. SQL Server has this, SQL Azure has this, Synapse Data Warehouse has this, all the different flavors of managed instance have this, all the flavors that you would know as SQL have been running in batch mode, and it's been there since, in some form or another, SQL 2012. And we've been making it better each release since SQL 2012. And one of the main reasons I wanted to give this talk is we sometimes go and we'll show a benchmark number. We won't actually sort of peel back a little bit and give you a sense that we actually are making each version better each release. It's not just that we're tuning it against whatever microarchitecture version is there. We also are doing algorithmic changes to also make SQL go faster as we go through each iteration of our product that we release. So for those that haven't been up to speed on ColumnStores typically do compression on all the values, and you can often get 10x savings in space. And then when you run queries, the query execution engine, batch mode, can often run 10 to 100 times faster for many workloads. So if you're trying to run big report queries, then this is a perfect thing to do that, because it basically changes what kinds of problems that you can solve in reasonable time. Because once you get to the point where you have to go get a cup of coffee to wait for this answer to come back, it sort of changes your workflow. And our goal is to try to give you something that works really efficiently so that you can just keep asking questions quickly instead of having to spend tons and tons of time trying to wait for answers, except for very, very large scales. So batch mode is designed with many of the ideas. Oh, is there a question online?
We have a question.
I don't see it.
No, it's coming up for some reason. Will case/switch statements create conditional branches?
The question is, will case/switch statements create conditional branches? Great question. The short answer is yes. However, yes asterisk. There are different things that you can do, but I'm going to translate the question a little bit. In SQL, we can run some parts of a query in batch mode and some parts in the legacy row mode engine. The legacy row mode engine will often go to the traditional expression service to go run logic. If it goes and does all that, then yes, it has exactly the property that I was describing earlier. There's actually has more properties than that, but there's overhead of the expression service, and you have this conditional branch issue. In the x86 instruction set, there's actually a optimization for conditional branches that can avoid branch misprediction penalties for one specific instruction. So it has a special magic instruction where you can say, hey, I want you to move either a 1 or a 0 to this particular place, depending on this, without changing what my next instruction is going to be. So there are some ways to optimize it if you get down to the level of the assembly. However, the traditional row mode engine was not attempting to do anything like that. I have not personally gone to go check if batch mode with case statements is optimized or if it tries to get down to the level of using that particular instruction. But let's just say that's the sort of thing that I would do and will put on my to-do list when I get home. Does that make sense? Any other questions while we're here? Okay, great. Thanks for the question. All right, so batch mode stores things in a slightly different way to try to basically have a compressed format that's really efficient to query and to get you back answers in an efficient manner. And it does so by leveraging the fact that many queries are doing like summation or aggregation to say, show me how many sales did I do by store over the past month for my retail business. And that then returns a lot less data than it tries to process. So it tries to figure out, how do I process that data very, very efficiently? And how do I make sure that when I do so, I'm using the fewest number of instructions possible, the fewest number of branch misprediction misses, the fewest number of memory accesses, et cetera. And we do that by trying to batch things up. And so instead of having a do one row, then get me another row and do things, it says, hey, I've got order 1,000 rows. I want to go through and do the same operation on 1,000 rows in a sequence, knowing that I'm going to do 1,000, not asking, am I at the end of that loop yet? And in so doing, I know that I can get the CPU to run more efficiently on average than I can if I were not to do so. So doing things in batches as opposed to row by row lets us kind of rethink a number of algorithms. And so we have a whole separate execution engine that tries to do this for running your queries. And the data structures are also set up so that we can be really careful about, okay, how much memory do we need to load in these 900 values? Do I need to see the whole row or just that column? And as we start to look at, if I'm trying to batch things in a CPU that has this large super scalar design where it can execute instructions in parts in parallel, how do I layer what I'm asking the CPU to do down into a form so that it can go as efficiently as possible for every single cycle of the CPU without stalling very much? And when we have tools from the processor vendors that let us go measure every one of these things, and we can go look at different approaches to implementing algorithms, and then we can figure out how do they affect the cache hierarchies, how are they using the CPU, are they bottlenecked on a particular resource, can we rethink how we structure our code or how we're asking the CPU to do things so that we leverage what it can do best. And that's the sort of work that, on a good day, I get to do for fun. Okay, this slide describes a little bit about row mode versus batch mode. So if you were to go back 30 years and look at a database textbook, you would see this picture roughly on the left where you'd say, hey, I want to do an aggregate over a filter over a table scan. And it would start at the very top and it would say, yep, get me a row from the hash aggregate. And it would say, fine, get me a row from the filter. Okay, get me a row from the table scan, send it back to the filter, and it would go, oh, does it qualify the filter? Is it greater than 10 or whatever? Nope, okay, throw it away, get the next one from the table scan until I find one that actually qualifies. Give it back to the hash aggregate. The hash aggregate would be great. Am I done? No. Get another row, continue. So it tends to jump up and down across these operators in terms of how it's built. Because back when you first had early database systems, you had very little memory in main memory. You had very little CPU processor speed. Disks were extremely slow. And that was pretty much all you could get to work. That was the model. And when we built SQL Server, that was row mode. That's basically there, and it works fine. But it's not optimized for these super scalar CPUs with deep caches because it's constantly basically thrashing on that level 1 instruction cache. It doesn't have enough instructions that fit in that cache, and it therefore has to go back out to more levels of cache in order to find instructions to be able to keep executing that approach to running queries. This design is called the volcano model, for those of you that want to go look it up in any of the academic literature. And so when we did batch mode, which was roughly 10 plus years ago, we went to a different model. Basically, think of it as a model like a train would work. You have all these different box cars, and you want to push them through one at a time doing operations. So I would take a bunch of rows and say, I'm going to do all the filters. So I would just get rid of all the rows that don't qualify, and I'll just do the filter on the 900 rows. Then I'll do the aggregate on the 900 rows. Then I'll get another boxcar and do the same thing over and over again. So I'm trying to take a large chunk of rows, and the chunk size is important, but we'll get to that in a second, and then push them through each of these operators so that level 1 instruction cache is extremely hot, meaning we're not having to go back out to main memory to get the next instructions, and we're able to go really think through how do we optimize each layer of cache. At the time that we did batch mode, the size of a batch was roughly designed to fit the level 2 cache of the CPUs that were there at the time. I have a little funny aside story I'll tell since we're not late on time right now. When we were building what became SQL Server 2005, we had a problem because we had a whole bunch of features that went into that. And for those of you that had been using SQL Server at the time, the release before was SQL 2000. And usually we release a version of SQL Server every 2.5 years. And those of you that are good at math will know that 2000 and 2005 are not 2.5 years apart. So we had a lot of features that were going into that whole bunch. It was a very big defining release. But one of the challenges we had was we had a model for how we did performance testing. So the amount of code in SQL Server had grown substantially from 2000 to 2005. And when we started running the performance tests, we couldn't match the performance of SQL 2000. We were really upset because no matter what we did, it was just a little slower, right? We would go and try building tools to look at the cache lines and figure out where the structures were. We restructured things to make them more efficient. And after months and months of this, we said, you know what, the lab has a bunch of perf machines in it and we can't make them go faster. Why isn't that the case? And the real answer at the time was the working set, the number of instructions that we needed to make SQL Server work had gotten much, much larger, and it didn't fit into the cache sizes for the machines that we had in the performance lab. So we tried fixing this for a while, and everyone, all sorts of smart tricks. And the right answer eventually was throw out the performance lab, buy newer hardware for the performance lab, and now we're faster. So if you ran SQL Server 2000 and SQL Server 2005 on the new hardware, SQL Server 2005 looked great. But that really boils down to the kinds of details that you have to get into to understand how do you make something run fast on a piece of hardware. You have to understand what you're bottlenecked on, and how do you think through designing your code to avoid those bottlenecks. Same problem applies to this level 2 cache. The whole reason we picked the batch size to be roughly that size was it fit, and therefore you would have fewer level 2 cache misses, which was a major determiner of your query performance at the time. Okay, so when we built batch mode, we didn't have every single operator built. We had many of them built, but not all, and we've been expanding that set over time. So we have the ability to fall back to row mode whenever we don't have full support to run the whole query in batch mode. And as a result, you end up having sometimes version X of SQL Server would work really, really well, but then version X+1 would come out and there'd be a new operator there, and it might make existing queries go a lot faster once you adopted it. We actually ended up building a feature to say, hey, if I'm running a big report query over a row store, a B tree, like a regular index, can we convert it to batch mode so that we can run that? Because it does often about 10 times faster, but it isn't 10 times faster for like 1 row or 10 rows. You need 1,000 rows or more often to get the payoff of doing the translation for it to actually make sense. So when we went through and built that feature, that was one of the algorithm's heuristics was, you need at least 1,000 rows for us to bother trying this, and then we'll work on trying to figure out, can we do the work to do that? There's a question, please. How do you handle different CPU manufacturers' generations with different properties of instructions? How do you optimize for each? Great question. Let me try to answer this in pieces. So when Intel adds a new instruction, the instruction set has a set of required instructions and a set of optional instructions. And so you can go and run a special instruction to say what optional instructions does the CPU manufacturer support for that chip, and then you can decide to use it or not. So SQL Server will do that, and then some instructions are limited only to Enterprise Edition in the on-premises version of SQL Server, so there's a business model piece there. We go faster on the fancier and more expensive version. And then we have a meta question, which is, well, does, say, AMD and Intel perform the same on the same instructions if you use these optional instructions? That question is a much harder question to answer, and the answer is that we go and look at each vendor's newest products and try to figure out what they do well. We give them feedback before they release their CPUs on where we feel like they could do better, and then we continue to work with them, and sometimes we will tune things based on each microarchitecture version. So for example, the AVX 512 work, which I'll talk about soon, that I shipped in SQL 2022, I recommend only in the latest microarchitecture version, so Ice Lake and above, for Intel or Genoa, which is the latest AMD server CPU, because those are the ones that have the good enough support so SQL will run faster versus using earlier versions of their optional instructions. So ultimately, there's no simple black and white answer on that, but there is a model that we use to try to figure out how do we recommend to people what to do. Any other questions before I move on? Okay, great. Okay, so now that you understand the rough idea between batch mode and row mode, I want you to understand some of the challenges that we face with each in terms of what works well and what doesn't work well. One of the recommendations that you'll often see when you're using earlier versions of SQL Server is that you might want to set max DOP, or the number of concurrent threads for a single query, to be like 8 or 16 at a maximum. And the reason for that was because of how the way that each of the modes for running parallel queries would scale or eventually stop scaling as you added more threads into the query. In row mode, we would basically do parallel queries by saying, yeah, we'll take and split up what we're joining or what we're aggregating statically based on a histogram of what we think the data distribution is, and hope that those are about equal chunks. And then we would run the processing, and as you can see here in this picture, I made it so that it was slightly skewed, that 3 of 4 threads would run in reasonable time, and then 1 thread would take a really, really long time at the end, and that meant that your query ran as fast as the really, really slow thread. So often, the amount of work to go and send data across threads and the issues with how the parallel model was originally designed meant, excuse me, that you didn't really have the ability to have perfect scaling. So after DOP 8 or DOP 16, you would end up being in a position where it didn't necessarily provide more value. You were just wasting CPU cycles doing the same amount of work. In batch mode, we went through extreme lengths to try to avoid this problem. We figured out how each operator could make progress on part of the solution without necessarily having to talk cross threads or how to talk cross threads very much. And we optimized how they talked across threads to try to make sure that we didn't have very much blocking. And so we ended up with a model where we said, yep, each boxcar will just do things against a local thread for a while, and then eventually we have to talk across threads, but we'll defer that as long as we can so that we can try to do as much local processing and therefore scale better as you add more and more threads. So when you're running in batch mode, you often don't need to worry about what the max DOP is. In fact, you often get better scaling for larger problems the more threads you add. I won't say there's no limits on this, but conceptually, it does really, really well. And I'll show you a picture of this. This is an example of what linear scaling would look like, is that gray line. And then this is one of the operators that we tested out internally to show how it scales almost linearly as you keep figuring out how to throw more cores and more threads at it. So this, at the bottom, is kind of hard to read, but at the right-hand side here, it's 72 cores. So we have the ability to make one operator scale to DOP 72 efficiently. Again, you should test your workload. I'm not telling you to go set your workload to DOP 0 on all scenarios, but there's a lot of work there that means that you don't have to necessarily, depending on what you're trying to do, just use up to 8 or 16 cores and then stop. We can, depending on the types of applications you want to run, you can potentially go and run many, many more. So you have the option to run with more cores to go faster in more cases. Okay, so now that you've kind of figured out some of the magic, I didn't go through every single technical detail. We keep some of them to ourselves, of course. I wanted to cover how we measure performance. This is from the TPC website, which is a benchmark that we use to measure SQL Server's performance. And the way that this works is there's different scale factors that you can publish. It's an industry standard benchmark. Every vendor can go and go out, every database vendor can go do this. And it typically works that you have a hardware solution that you have to buy and a software solution that goes with it. And I wanted you to call out, the first one is 1,000 gigabytes or 1 terabyte. The next one is 3 terabytes. And as you can see here, the very first number on the 1 terabyte number is Hewlett-Packard Enterprise, and it has this QPHH number, which you should think of as like a car's horsepower, effectively, the analytics horsepower. It has the time that it was available, and you can notice here, this is SQL Server 2022, Enterprise Edition, 64-bit, and the date was submitted on 11/3. So the date format here is the US format in this case. So November 3rd of last year. This is when we shipped SQL Server. So you can see here, we have the top benchmark spot for the 1 terabyte TPCH number. We also happen to have the second and third spots, which are run on 2019. We ran those on Linux, just because Linux was relatively new then. But overall, they're running the same basic analytics engine. They use the same architecture that I've described to you in this talk. So I will point out that my competitors are not on the 1 terabyte number. I'm not quite sure where they are, but they're not there. Maybe we should look at 3 terabytes. First number, also SQL Server 2022. So we did a 1 terabyte and a 3 terabyte number when we launched SQL Server, and you can see both of those numbers are there, and they're both faster than the number before. And you can often see that they're sometimes substantially faster than the number before. And it's not just because the processors have gotten better, it's because SQL has also gotten better. It's a partnership. And then, oh yeah, by the way, the rest of the 3 terabyte numbers, also SQL Server, SQL Server, SQL Server, SQL Server. Anyone else use other database vendors? No? A couple? Yeah? Your fault. Oh, wait, there's more. This is the 10 terabyte number, and the 30 terabyte number, and the 100 terabyte number, and we own all of those as well. Now you know why I like getting up to go to work every day. I won't speak for my competitors, but I will say that we spend a very large amount of time making sure that we're doing this so that you can see a public, disclosed, audited benchmark number for our product when you buy it. right? So therefore, you can see, yep, you can go run this test yourself on exactly the same hardware and replicate these results if you want to. And that's the whole point of these benchmarks. We haven't seen as much out of our competitors publishing them. It might be because they're not as fast. It might be because they don't want to. But ultimately, that's the space that we like to play in. So we want you, when you buy SQL Server, to realize you're getting the best deal for your money, and you're also getting the best performance, if that's your goal. And these configurations, sometimes we'll do one for performance and one for price perf, just to show you can tune your optimization of what you're trying to buy the same way. Same engine works in our cloud. So Synapse Data Warehouse and SQL Azure also are using the same base engine. All right, the next thing I wanted to bring up is one of the reasons that we also go faster, and this is a bit harder. So one of the optional instruction sets that they have is called AVX, and there's different generations of AVX instructions. There was SSE 4.2, sometimes called AVX 1, that came out roughly 10 plus years ago. It uses, instead of 64-bit registers, it uses 128-bit registers. AVX 2 came out later. It has 256-bit registers. And then AVX 5.1.2 has been out for several years, but it's been sort of slowly being deployed in fullness, and it has 512-bit registers. And programming AVX is fairly hard to do. I taught myself during the pandemic while bored, stuck at home, and then ultimately turned my attention to SQL Server and did the work that went into SQL 2022 to turn on AVX 5.1.2, and that is the reason that we won on these benchmarks. Ultimately, you have to be very, very careful how you structure your code to be able to take advantage of these, because if you do it the right way, it runs really fast. If you don't, then it goes slower. And so you have to really just think through, okay, how do I structure my code? How do I structure my algorithm? Sometimes you have to rethink what would be the normal way to write a piece of code in C to be able to actually avoid some of the limitations. Ultimately, if you don't do it right, for example, or if you use too many of these instructions, then it throttles the CPU frequency down, and then the whole chip goes slower, not just the one core that you're running on. So you have to be extremely careful. But what you're really doing is running n things at a time. And I put an example on the right-hand side of basically adding up numbers. So if you want to go and just add up numbers, the left-hand side would be if I did it without any vector instructions. And then, as you can see, I can go roughly almost 10 times faster with AVX1, and again, 2 times faster with AVX2, and again, another 2 times faster with AVX 5.1.2. So the more that we can go and rework our engine, we can get this to be the way that you get the performance benefits that you need in order to actually help us win those benchmarks. 2 other little things I'll show you. I got special permission, because these are not out yet, to kind of talk about this today. We have been working on various happy path optimizations in batch mode to make it go faster, so that when you're running your code, you get advantages of this. So this is one that we've been doing on our team. It will ship soon, where we said, yeah, let's go take batch mode. And when you're running built-in functions, some of the built-in functions we've tuned to kind of run fast in batch mode. Others, we kind of revert more or less to the row mode model. And so we went and took some of the functions that we've been working on, and we said, let's go change those and see how much faster we can go. This is greatest, which my team built and added in SQL 2022. So we said, let's go make that go faster. And so we went through and did 7 million rows, running greatest across 6 arguments for 6 columns. And you can see here we went from, roughly 275 for seconds to, I think it was 120 seconds or something for this synthetic example, but it's trying to isolate the performance. And we have a series of these that'll be coming out that will basically make it so if you're running lots of built-in functions, your batch mode versions of those functions will go faster. This didn't ship in SQL 2022, but it would go into later versions of SQL Server. Another example, this is TPCH Q1. The TPCH query has 22 queries. The first one is an aggregate query, which has a bunch of aggregates. And we did some work there to speed it up with various optimizations using batch mode improvements. And as you can see here, we went from roughly 850 milliseconds for this query at this scale factor to basically 500. So maybe 30, 35% faster. This also is not out yet, and it will be soon. But this is the kind of work that we're doing. We typically wouldn't go and market these because they're not by themselves giant things with names, but these are the kinds of work that my and other teams within the SQL org are doing to try to make batch mode faster each and every release so that you don't have to think about it. We just make it go faster if you're programming on batch mode. And then finally, I just wanted to let you know that our goal is to keep doing this so that you just are able to bet on SQL and make sure that when you use it, we're looking at your workloads to try to figure out how to get the most out of those CPUs. If you have cases where you think we could do better, I would love to see examples. And that's kind of the whole purpose of this talk. I wanted to get you thinking about the kind of work that we do to make your queries go fast. And thank you very much for your time. Okay, I'm done.